where we left off. I really hope we can get through this whole part because it would just make everything better. So remember that electrons we use arrows for. Each box represents what we call an orbital. We can put 2 electrons in each box, but they have to have, if there are 2, they have to be an up spin and a down spin. That's -1/2 and +1/2. This thing about subshells, think of it as kind of as how do I say, up over here. Okay, I kind of did the whole n is equal to 1, that's the principal energy level. We can have 1 subshell. N is equal to 2, we have 2 subshells. N is equal to 3, we have 3 subshells. And then the goofy thing, sort of goofy I think, is you have to, if you learned this before, whenever you see an S, that actually has an L value of 0. Whenever you see a P, it has an L value of 1, D, L value of 2, F, L value of 3. Because actually, and I'm going to show you, we have some rules for these. Okay, I'm building up to being able to like point to 1 electron. For instance, I've been picking on carbon. Carbon has 6 protons in its center, so if it's neutral, it has to have 6 electrons. We're building up to being able to point to 1 specific electron around the carbon atom and say all of this stuff about it. What principal energy level is that electron in? What sort of subshell? That's the SPDF thing. We need to talk about these 2 quantum numbers today. M sub L, I'll show you, you guys will do fine with it. But M sub S, remember we said the values are just possible +1/2, -1/2. All right. So it's all about rules, and this is a review slide. We said that in theory, and it's true, actually I shouldn't just say in theory, but our N values could go like forever, okay, our principal energy levels. The deal though is that we're focusing on electrons as they are in their ground state. So we're not talking about excited state in here. We're just talking about ground state. So there will be a limit to how high it ends you guys have to worry about. The L value, I already told you, that's the SPD and F thing. So like I said, you're going to need to kind of translate. 0 is S, 1 is P, then we have D, and then we have F. Now there are actually higher subshell types, but we don't have to actually worry about them as we find homes for electrons, and electrons are in their ground state. Notice though that we can, in any given N, and I'll kind of do this up here. Let's see, will this work? Well, I have an example coming up. But see if this works for you. I can't draw up there, but I'm going to go N is equal to 5. So actually you would have a 5S, a 5P, a 5D, a 5F, and you get a 5G then. Like, gee, really? Yeah. Okay, and let's see. If we do the pattern of odds, we go 1, 3, 5, 7, 9. 9 orbitals, okay? But we don't actually have to put electrons there as they are in their ground state. It feels weird, but it's true. But it's there. So finally, I think we're on to a new slide. I just kind of want to take a running start at this. So whatever energy level N actually dictates how many L values you can have. Because our L value, we said, the rules are, they start at 0, they're integers, 1, 2, 3, all the way up to N minus 1. So whatever your N is, you take -1, and that's the upper bracket of these integers, okay? So for instance, if we pick on 1, N is equal to 1. N is equal to 1. Take the 1, plug it here. 1 minus 1 is 0. So you got 0, 1, 2, 3, 4, 0 all the way up to 0. So that's why you only have 1 possible L value. So that is 0. Okay. That's how those rules work. Well, let's go up to 2. Well, you see 2, I had a 2S and 2P, but how does that work? Well, remember the S and the P are L values of 0 and L value of 1. So, all right, so n is equal to 2, plug it. So I go 2 minus 1, that's 1. So I go 0, 1. Okay, there's my 0, 1. See how that works? Yeah, that's it. And so a 0 is S and a 1 is P. So, all right, n is equal to 3. Well, you see on kind of my, I call this the onion sometimes, kind of the layers, the possible energy subshells. I've got an L value of 0, an L value of 1, and an L value of 2. Because when n is equal to 3, 3 minus 1 is 2, so you got 0, 1, 2, etc., etc. Okay, when n is equal to 4, you have all the way from 0 up to 4 minus 1, which is 3. So, yes, you can kind of see those, etc. Now, n is equal to 5. I did this one over here. You pick up a G type. Okay. So, it looks like this. Right. So, another way to look at it is the number of subshells. Will this work for us? The number of subshells we have at a principal energy level is equal to that principal energy level number. 5, we had 5 possibilities. N is equal to 2 possibilities. N is equal to 3 possibilities. That makes sense because it's 0 all the way to n minus 1. So the math all works, okay? All right, and remember that even though here beginning n is equal to 5, we pick up a G type, which would have 9 boxes, 9 orbitals following the pattern. We're not going to, electrons can be excited there, but in the ground state, they're not there. Makes you want to find heavier and heavier elements, so we do go ahead and occupy those. All right, so these are things that you're already new or are kind of picking up on. As I've drawn them here, I'm going to erase this, so this is kind of, makes it kind of messy. As I've drawn them here, I've been careful that within the same principal energy level, like this 3, I've drawn them, and this is increasing energy. I've drawn them with the lowest energy, more energy, most energy, okay? Now, again, on Friday or Monday, I'm going to try to have to unscramble that a little bit for you guys using what I call the arrow diagram when we look at different energies, different principal energy levels. But within the same principal energy level, we have this trend. Okay. All right. So those are 2 quantum numbers. This third quantum number narrows it down to the orbital, the box. And that's kind of why I wrote these over here, okay? Just generic S, P, D, and F. We need to label each box, and that's where the M sub L, or the magnetic quantum number, comes from. The rules for the magnetic quantum number, you can look at it 2 ways. These are both saying the same rule. What I like to do, if it's okay with you, is I'm going to show you what this looks like. So this says for every subshell type, you will have M sub L values from 0, plus or minus 1, plus or minus 2, plus or minus 3, all the way up to plus or minus L. Well, if it's an S type, L is equal to 0. So you got 0 all the way up to plus or minus 0. Kind of weird. So actually, if it's an S type, this guy right here, this M sub L value is equal to 0. Works. Now, let's go for the P-type subshell. And this could be a 2P, 3P, 4P, anything. We know we've got like 3 orbitals. We need to give those an M sub L value. This is my favorite way to do it. I pick the middle one, and I go that. I'll just do this. These are M sub L values. I pick the middle one and call it 0. M sub L values. I'll call this one 0, and I'll call this one plus 1, and this is minus 1. So for P-type, L is 1. So I go from 0 to plus or minus 1. 0 to +1 and -1. Otherwise, I go from the -1 through 0 to +1. Those are all same. Those are both ways of stating the same rule. So then here we go. This one, when L is equal to 2, the D type, our M sub L values, I find the middle one, I put that 0, +1, +1 plus 2, and I put -1, -2. For L is equal to 3, I go, my M sub L values look like this. I'll put 0 in the middle, +1, +2, +3, -1, -2, -3. So there are ways of getting down to the nitty-gritty. And I already kind of told you the quantum numbers go, you know, the N is the most broad. The L kind of gets it down to a subshell. The M sub L says which orbital within that subshell it is. And the last one, M sub S, says, is it pointed up or is it pointed down? That's it. 4 quantum numbers. Okay, so each value of M sub L is associated with a box. The box is an orbital where you can hold 2 electrons. All right. Woo. How many different orbitals can be found in a particular subshell? All right. So I kind of feel like I've been talking about this already. So a particular subshell, if we pick an S-type subshell, 1 value. A P-type subshell, 2 values. Okay? A D-type, 3. P-type, 3 values. A D-type, 5 values. And it's consistent with that rule that we talked about, or that was shown on the previous slide. Sometimes, like when I'm working an answer key for this Unit 4 exam in here, I will go ahead and jot these down in the margin because I picture them better. In your homework and on the test, I'm going to ask you questions about allowed quantum numbers. And to me, the best way to answer those questions is to be firm in kind of the way it works, the way quantum numbers work. And I'm a visual person, so I like to kind of write it out and then kind of see, oh yeah, I get it. You'll see what I mean when you do some of the homework. All right, number of orbitals can be found at any principal energy level. So if you know the principal energy level, that it governs how many subshell types, and within the subshell types, you know that you have these rules. Okay?
So these don't change?
No, they do not change. No. Yeah. It's nice things that don't change, isn't it? Yeah, I agree. Okay, so if we pick on n is equal to 3, and again, so how can we answer this question? Well, if you have doodled something like this in the margin, you're like, n is equal to 3, well, I know what that looks like. Okay, otherwise you're like, no, what does that look like? Okay, it's just a thought. Okay, so when n is equal to 3, then we know our L values are 0, 1, and 2, and of course, that corresponds to S, P, and D respectively. And then you know for the S you have 1, for the P you have 3, and for the D you have 5. And sometimes when I'm doing this over here, I actually will go ahead and write 1 box, 3 boxes, 1 box, 3 box, 5 boxes, 1 box, 3 boxes, 5 boxes, 7 boxes, you know. So when n is equal to 3, if somebody asks you how many orbitals, so orbitals, hopefully you're thinking orbitals, we're talking for boxes, orbitals. So if you did that, you could go like, dang, I'm picking 1 here, 3 here, and actually 5 here, and I can literally count those. So you got 5, 6, 9. 9 orbitals, and that's the answer here. In the end, or one of the last slides, I'm going to kind of tell you some shortcuts to a question just like this, and it is so cool. A shortcut to knowing how many orbitals you have in a principal energy level is n squared. where n is your principal energy level. So check this out. So n squared, n raised to the second power. So 3 squared is 9, 2 squared is 4, 4 squared is 16. Okay, and actually that'll work for you. Kind of a shortcut. Either way. I know, shortcuts are good. Yeah. So that's the number of boxes or orbitals. And this is kind of what we've been talking about. So here we have, these are your principal energy level n's. These are the allowed values of L's, where 0 is S, so 1 is P, 2 is D, and then 3 is F. And then over here, these are your M sub L values. These are like the little assigning orbitals. And so does 4 have 16? We got 7. 5 is 12. 16. All right. Cool. Oh my God, so fast. Oh my gosh. But I don't think I'm going too fast because we're almost done. There are some more important things. I have a lot of pictures here. So the orbital, electron orbital is, remember, keep your wits about you, it's like the region outside of the nucleus where you would expect to find the electron. And if you're like me and most people, you think, well, I have the nucleus, and then I have electrons, and I make a sphere. But that's not what the shape always is. That's the shape we think of most. Okay, so they have different shapes. If it is an S-type orbital, it's going to be spherical. If it is a P-type orbital, it's going to be dumbbelled shaped. So this is spherical shape, and this is dumbbelled shaped, and this is just craziness. Okay, I put a question mark. We know what they look like. I just can't describe what it looks like. Okay, so here's kind of the spherical distribution of where the region of, what do we say, like 97 or 99% probability of finding an electron. Or how probabilities work is, can you find it outside that region? Yeah. Okay. This is actually, looks like a Tootsie Pop, doesn't it? Think of that first blue one as being this 1s. Think of the next red one as being 2s. And then the next blue one is being 3s. So they're all spherically shaped with the nucleus in the center. The higher n, the 3s, is going to be farther from the higher energy, and actually the electron will reside farther from the nucleus. So there's S. And I said P is dumbbell shaped. I don't know if that looks like a dumbbell to you guys. So P, and it's kind of fun because it's consistent with what we've been talking about. If it's a P-type subshell, it's going to have 3 orbitals, 3 M sub L values. Check it out. M sub L minus 1, M sub L 0, M sub L plus 1. So those 2 lobes actually on either side of the nucleus. So if the nucleus of the atom is here, we have actually lobes here, which is 1 orbital. 2 electrons will occupy 1 orbital. So those 2 electrons in that orbital are kind of buzzing around like this. And then it's kind of nice, this whole spatial thing, because if you go 3D, you have an x-axis, a y-axis, and a z-axis. I'm not sure, probably this is z, x, y, I don't know. But you have 3 axes. At the center of the axis is literally the location of the nucleus. So you have dumbbell here, dumbbell here, and dumbbell here. 3. That's nice. Then we get to the D-type. Here you go. So D-type, we must have to have 5. C5, 1, 2, 3, 4, 5.
I should name it the egg nest shape.
The egg nest shape. That's what it looks like. Isn't that crazy?
That's nuts.
That is just bizarre. And you can see the M sub L values of -2, -1, 0, +1, +2. That's 5. And here we go. Here's F. And then how do they find these things out? These are spatial things, spatial distribution of a pair of electrons. Really? So it's interesting. So yeah, most of us picture electrons being in the sphere. But with some of these, with all of the 3p orbitals, the probability of finding the electron close to the nucleus is 0. And it's more farther out. So back to the S. Specifically, if it's close to the nucleus, lowest energy, you're talking 1s instead of 2s or 3s. Here are the dumbbell shape of the P's. This is if you were to take the p orbitals, this is if you were to take these 3 electron orbitals and combine them all together, this is what they would look like. Because you figure you have them along the x-axis, the y-axis, and the z-axis. And that's very busy. And remember what we're talking about here, and I'll pick on the p just to kind of make sure we're still on the same page. So for every orbital, I can put 2 electrons, and we're going to talk about this one last time. If I do put 2 electrons, I better have one with an up spin, one with a down spin. That actually represents a plus 1/2 and a minus 1/2. So if each arrow is an electron, what are you talking about? Like 6 electrons there if you completely fill it. So all I'm saying is in this busy sort of spatial region, you have 6 electrons that are doing their thing. All right. This is back to, we already looked at this a minute ago, but this is your D. So if it's D, we must have 5 orbitals, and here's what they look like, the nested eggs. This is the F. And this is showing you one of the 7F. So here we go. All S's are spherical. They all look spherical to me. But I would describe, for instance, the 3s as being farther from the nucleus, higher energy versus the 1s. Okay. When n is equal to 2, you pick up the p type. So we have a 2p and a 3p. Again, we can compare the 2px and the 3px, and they're oriented the same way, but the 3px is farther from the nucleus. And at n is equal to 3, we pick up the d, and there you go. So I mentioned that if it's a p, the way just visualizing the dumbbell shape, they connect at the nucleus, and if the colored region represents finding an electron there, they basically, the probability goes down to 0 at the nucleus. It creates what we call a nodal plane. So if I can take like a sheet of paper like that and basically go between, or go, in this case, within my one orbital and have a 0 probability to find an electron there, that's a nodal plane. So we have the nodal plane this way, nodal plane this way, and a nodal plane that way. Okay, so just to kind of finish up, I've been already talking that way back at the beginning of this part, we said that you can put 2 electrons in an orbital, but if you do that, they have to have opposite spins, and that's our last quantum number. So, for instance, let's see, I'll pick on. Let me pick on this one. So I'm going to take this one and make it a little bit bigger. That's my 3s orbital, and I'm going to go ahead and do this. Now, for that one electron right there, I could go ahead and give its address. When we give addresses in your homework and on the test, they look like this. You give the n value, you give the l value, you give the m sub l value, and then you give the m sub s value. These are in order of most general to most specific. So for that one guy right there, I could say its n is equal to 3. Its m sub l value is equal to 0. Wait, sorry. It's 0. This 0. Oh, sorry. Its n is equal to 3. Its l value, I skipped l. Its l value is 0 because it's s, that's 0. Its m sub l value is also 0. And the fact that it's an up spin, usually we go up as plus 1/2. So when we talk about a zip code or a set of quantum numbers, that's exactly what we're talking about. Okay. And I have a few videos. I guess I do have a little video to show you, short, to kind of show you what I mean by the spin numbers. And it's potentially confusing. I mean, but you don't need to know. I don't ask a specific question, but this is kind of what's happening. I'm pretty sure, like dams on the river and such, they use water to spin, let's see, turbine. They spin something, and as they spin it, if you can go ahead and have electrical charge spinning, well, that creates electricity. So, but anyway, if I plug this in and have electrical current going on this copper wire, that actually creates a magnetism right here. Like I could put my I just think that's cool. Anyway, okay. What else? So Pauli's exclusion principle. It's a wonderful term to actually throw on your Unit 4 exam if I'm looking for something to see if students know what it means. Pauli's exclusion principle. Doesn't that sound like a good one? And it's exactly what we've been talking about, that if you have like an atom like carbon, 6 electrons, we could go ahead and write the 4 quantum numbers for each of those 6 electrons, and none of this has to be entirely correct, the same. Okay, and I hope you got this up here where I said if you're trying to give a zip code, you go from the most general to the most specific, and you will homework on your exam. Go ahead and give me the 4 numbers like that. So we kind of started out earlier in this part. We said that if you have an orbital, which is a box, which you're drawing like this, if you have an orbital, you can only put 2 electrons in there. And in part, that's because for the last quantum number, you only have 2 options. You only have a plus or minus 1/2. I can't remember if it's one of your homework questions in the previous edition or textbook maybe. But like if you had 3 possibilities for the M sub S, the spin, like if you had, I don't know, a minus 1/2, a plus 1/2, and a 0 spin, that kind of opens up possibilities. Then actually for each orbital you could shove 3 electrons in there. But we only have 2 in this universe. So since the S-type subshell only has 1 orbital, each orbital can accommodate 2 electrons. You max out at 2 electrons in an S-type subshell. So this last part kind of goes like this. If I, oh, by the way, I get kind of, it's not really lazy, but instead of putting like 2 tails on my arrows, I only put 1 tail on an arrow. So you're going to see that's my arrows. I know, that's just what I do. So you max out with 2 electrons here, 6 electrons here. How many electrons do you max out here if they're all filled? 10, you got it. 10 electrons here. How about up here? 14. Yep, I'm not going to do all that, but that's 14. So 10 here, 14 here. And actually, those numbers, the 2, 6, 10, and 14, those kind of capacities, whether you write them down or you're visualizing them, those are going to be important to carry into Friday's discussion on how do we place electrons as they're associated with an atom. Cool. This then are some little, I mentioned the n squared rule. Okay, this slide is getting to the n squared rule, sort of. So first off, how many boxes are there in each L type? Well, all you got to do is take 2 times the value of L plus 1. All it's saying is, if your L is 0, you take 2 times 0 and you get 0 plus 1 is 1. Okay, if your L is 1, 2 times 1 is 2, plus 1 is 3. Okay, so these are saying how many orbitals, and you already kind of got how many orbitals already. This one says, all right, if you know how many orbitals, if you want to know how many electrons you accommodate, just go ahead and take that times 2. So this is how many electrons you could have put in each subshell type. This just goes back to, you told me 2 electrons here, 6, 10, and 14, you know, etc. And this is the n squared thing I was talking about. So this is taking it back a step, and it's saying if you go to principal energy level, and on a test or somebody just in general wants to know, for that principal energy level, how many orbitals can I have? Well, it ends up being n squared. So that's where we got, for instance, when n is equal to 4, you could have 16. You'll have 16 orbitals by the time you have orbitals in s, p, d, and f. Wow, 5 squared is 25. So you're going to have 25 orbitals when you put, accommodate, or consider the 5s through 5g. Okay, so then, since each orbital can accommodate 2 electrons, for instance, if we pick on n is equal to 4, we have 16 orbitals. Well, each orbital is 2 electrons, so 16 times 2, that's 32 electrons. So that's how that works, 2n squared. Okay. So here is another rule that I haven't mentioned yet. And so up here, when I put an X through this, so why did I put an X through this?
Because they're in the same direction.
Yeah, they're going the same direction. That's disallowed. It doesn't happen. You won't, it disallowed. Here's another to see kind of how we do electrons around an atom. Electrons are located in orbitals with a maximum number of 2 electrons per orbital, and those electrons will have, electrons in the same orbital will have opposite spins. Oh yeah, I already did that. Orbitals are grouped according to subshells, with each orbital in the subshell having exactly the same energy. Degenerate orbitals, I like that term too for vocabulary. They're called degenerate orbitals. We're okay with that. Subshells of orbitals are found in different energy. That's the principal energy levels, n's. Okay, so yay. That does it for that part.